Hello everyone, welcome to video lecture series of design of steel structures. In this video, we are going to continue with the previous video problems only. Here the difference will be instead of single angle section, we are going to add up a double angle discontinuous strut. Correct? So numerical for the given numerical for the next strut design is calculate strength of discontinuous strut of length 3.5 meter. The strut consists of two ISA Indian standard angle. Again, both the angles are unequal angle sections. 150, 75, 10 at the rate 16.9 kg per meter with longer leg connected to gusset plate on both the sides. So the basic difference you need to understand between previous and this problem is for single angle sections you need to go with lambda equivalent value. Correct? Here you need to assume constants k1, k2, k3 depending upon the type of connection given, whether it is a single bolted or double bolted kind of connection. In case of double angle section, regular procedure is to be adapted, that procedure which you are adapting for design of regular compression member. Correct? So initially starting with the first step of given data. So for given data, calculate the compressive strength of discontinuous strut of length 3.5 meter. So length between the intersection is given as 3.5 meter. Here you need to understand the effective length calculated for a discontinuous strut is again depending upon whether it is a double angle section or whether it is a single angle section connected. So here in the numerical they are mentioning it is a double angle section on either sides of gusset plate. Therefore here you need to add up a value as 0.7 to 0.85. Correct? So suppose we will add up the value as 0.85. So length is equal to 3.5. So we will calculate effective length KL is equal to, or L effective equals to 0.85 into L, and that is equal to total value calculated is 2.975 meters. Correct? So from first data we have calculated effective length. For discontinuous strut double angle section is 0.7 to 0.85 times according to IS 800. Now the strut consists of I section, 2 ISA 150 75 by 10 at the rate 16.9. So from this particular data you need to write down the properties of your section. Correct? So properties such as for ISA unequal angle section 150, 75 and 10 is given. So initially starting with area of the section is given as 2156 mm square. Correct? Next data we are going to copy, that is radius of gyration rxx is equal to and ryy equals to. So rxx is given as 48.1, ryy is given as 19.9 value. Correct? Then next moment of inertia, so Ixx equals to, so here always you need to remember in your steel table horizontal axis is mentioned as your x-axis, and for calculation purpose always that horizontal axis we are treating as z-axis. So Ixx mentioned in your steel table is nothing but it is your Izz value. Correct? So Ixx is given as value is 499.1 into 10 raised to 4 mm raised to 4. Value mentioned in the steel table is in cm raised to 4. The next Iyy equals to, so that value is given as 85.3 into 10 raised to 4 mm raised to 4. Correct? Now again Cxx and Cyy. So Cg of individual section, this is your Cxx individual section and Cyy value. So Cxx is given as 53.2 and Cyy is given as 16.1. Here these details of gusset plate are directly mentioned in figure. If sometimes gusset plate thickness is not mentioned, you can assume that value as 8, 10, 12, 16, anything. Usually try to select the value which is mentioned in your steel table so as to reduce the calculations which we are going to do here. I will tell at the last what calculation you can reduce by doing this particular calculations. Correct? So Cxx value is equal to, that is given as 53.2 and Cyy value is given as 16.1. Correct? So likewise is the geometry for entire section. This is vertical y-axis for common total section and this is horizontal z-axis. Correct? Again with the help of yellow color chalk, individual CGs I have shown. This is particular y1 for this section and again y1 for second angle section. So the section is symmetrical about this particular vertical axis, symmetrical about vertical y axis, correct, and it is unsymmetrical about horizontal z axis. So this is the distance between two parallel axes, and here for calculating your combined moment of inertia we are going to see the parallel axis theorem, correct. So the perpendicular distance between the CG of entire section and CG of individual section, that we are going to calculate here. So here just by observation only you can see, as it is symmetrical about vertical y axis, in that cases for z axis alternate axis is not available. So here the moment of inertia is going to be directly double for a given value. For example, it is mentioned as Ixx or Izz is equal to 499.1 into 10 raised to 4. So combine is going to be what? Just multiplication by 2. So 2 multiplied by 499.1 is nothing but it is your combined moment of inertia about x-axis. Correct? So ultimately that is going to be greater value, and for calculation always you are requiring what? You are requiring lesser value. We have already seen that design compressive stress PD value, design compressive strength PD value is given as area effective into FCD value. So area effective is known to us, and second value is your FCD. FCD is design compressive stress. So this design compressive stress depends upon lambda value and buckling class. So what is lambda value? Lambda is given as KL by R value, correct, and buckling class depends upon your that table where A, B, C, D, these likewise 4 classes we have seen, correct. So for calculation of KL by R value, KL that is known to us already, we have calculated KL as 2.975 depending upon your continuity, whether it is continuous or discontinuous, it is single angle or double angle. So here it is a double angle section, therefore we are assume that 0.85 times of your given value, and it is equal to 2.975. Now remaining is the value of R. So this R is minimum radius of gyration, because when you are going to calculate this particular value as minimum, you are going to get a lambda maximum. So always you need to calculate lambda max, because for lambda max if your section is satisfying, for minimum value it is ultimately going to satisfy, as higher the value of lambda lesser is the design compressive stress. So in order to calculate maximum value, this should be your minimum. R should be what? Minimum. So radius of gyration is given as what? Under root of moment of inertia divided by area. Radius of gyration is given as under root of moment of inertia by area. So in order to keep your R as minimum value, your moment of inertia should be again minimum. So for calculating minimum moment of inertia, you need to consider two values: combined moment of inertia about your horizontal z axis and combined moment of inertia about y axis. So ultimately we have seen, if you are going to consider about horizontal x axis, ultimately double value you are going to get. So we will directly calculate the moment of inertia about vertical y axis. So that will be the next step. Now calculating IYY combine, that is for both the sections, and here we are adopting parallel axis theorem. So it will be Ig plus A into H square, correct. So as two sections are there, this is going to be multiplied by 2, correct. So this will be equal to 2 into bracket moment of inertia for y side. So moment of inertia for y side is 85.3 into 10 raised to 4 plus area of single section is 2156 into H value, correct. So difference between the section along y side. So this is the CG of entire section and CG of individual section. This distance you are requiring. So already we are knowing CYY value. CYY value is given as 16.1, correct. And this half value is nothing but what? It is gusset plate thickness by 2, correct. So 10 by 2 is nothing but 5. So 5 plus 16.1 is nothing but 21.1 value is nothing but your H value, correct. So I'll be writing that into bracket 10 by 2 plus it is 16.1 bracket square. So this value is going to be combined moment of inertia IYY is 3.62 into 10 raised to 6. 3.62 into 10 raised to 6 mm raised to 4. So combined moment of inertia. So this will give us what? R minimum. So R minimum is equal to under root of IYY calculated divided by area is equal to. So as this area is, or as this moment of inertia is twice, area is again going to be multiplied with 2, correct. So under root of 3.62 into 10 raised to 6 divided by your area is 2156 into 2, double area. So R minimum I am going to getting value as 29 mm. 29 mm. So this is the least radius of gyration, correct? Now last step, KL by R minimum is equal to lambda equals to, so KL value is 2975 in mm divided by calculated least radius of gyration 29, and this is equal to, we are getting value as 102.58. 102.58, correct? So as we have seen, there are 4 buckling classes A, B, C, D, E, and according to table always angle sections are coming under category of C, correct? So referring table 9C for design compressive stress, and that is given on page number 42, correct? So table 9C page number 42, 102.58, this is lambda value and buckling class C, correct? So table 9C page number 42, correct? Yes, this is page number 42. So on that you can observe that values are given, your values of slenderness ratios are lesser towards top side and they are increasing towards your bottom side, but opposite is the case for your FCD value, correct? So our value is ranging between 102.58 is the value, so it is ranging between 100 and 110, correct? So initially I am writing lambda value here, so it is 100 and second is 110. I am requiring value 102.58, correct? So FCD value is to be calculated for slenderness ratio 102.58, which is intermediate value of 100 and 110. Similarly, copy FCD for FY250, correct? For FY250 FCD value you have to copy, correct? So that values are given as 107 and 94.6. 107 and 94.6, and you need to calculate value at this location, correct? So simple cross multiplication we have to do. Initially calculate the difference for these two, 110 and 100, that is nothing but difference of 10, for which 107 minus 94.6, what is the difference? It is equal to 12.4, correct? So for total difference for this particular left side, right side value is 12.4. Now you need to calculate for 100 minus 102.58 means 2.58, correct? 102.58 minus 100, this value, that is nothing but 2.58. For that, suppose x value is there, so cross multiply 10 into x equals to 12.4 into 2.58, so x will be equal to, so cross multiplication, that value is 3.199, 3.199, and values are decreasing. So 107 minus calculated difference 3.199, you are getting value as the answer is 103.80, 103.80 MPa. So this is the design compressive stress, correct? So putting that value into last step, design compressive stress PD is equal to 2 multiplied by, because 2 angle sections are mentioned, correct? 2 ISA, and area of single is 2156, so 2156 into 2 multiplied by FCD, FCD value is 103.50, sorry 103.80, again divided by 1000, so the final answer is 447.58, 447.58 kilonewton. Here the answer is completed. So difference between previous videos numerical and this numerical is what? In case of that single angle section, always you need to consider lambda equivalent value, and you need to calculate the design compressive stress FCD, where you are not going to adapt tables, correct? Already we are referring regular process of design of compressive, and in case of second section, here you need to adapt your table values by calculating your slenderness ratio according to your given length, correct? And for that length calculation, for double angle discontinuous strut, value is to be adapted as 0.7 to 0.85. For current numerical, we have adapted as 0.85. Usually in some cases these sections may fail in case of design problems, so try to adapt the value of in 0.7 value, so you will be getting greater slenderness ratio, and for greater slenderness ratio your value is going to be satisfying the given loading condition. So here the numerical is completed. This type of numericals may be asked in your in semester or end semester examination for 6 marks. So in the next video, we will see some of the problems on rolled sections. Thank you very much.